morning, everyone. It's a pleasure to introduce today the CIBM talk for visitors professor. And we have the pleasure to have today Professor Franco Pestilli, which is professor at the University in Psychology and Neuroscience at the University of Texas, Austin. So Dr. Pestilli research centers on two main pillars. The first is advancing our understanding of architecture and function of brain networks, and in particular white matter. And the second is leading the development of brainlife.io, which will be a key focus today of today's talk, which is a cloud computing platform that promotes scientific education, transparency, and rigor, with a strong emphasis on the equity and accessibility of science. Dr. Pestilli earned a bachelor degree from the University of Rome La Sapienza in psychology. Then he moved to New York University to work with Marisa Carrasco on attention and visual contrast, where there he completed his PhD. Then he continued for a brief postdoc at Columbia University before joining Brian Vandel's lab at Stanford University, and where he began his journey and his focus on white matter. He then launched his own laboratory at the University of Indiana, Bloomington, and started working on this idea of a platform that would promote the infrastructure for the analysis of MRI data. I've had the privilege to work with Franco for over a decade now. And I can say that in addition to the scientific contributions that he has made, to the numerous grants and awards that he has received, what stands out is his unconventional journey from psychology to MRI data infrastructure. And even more so, his generosity with time, data sharing, and mentorship. I've been the privilege of being one of his mentees indeed. And most of all, his incredible ability to make connections, not only between brain areas, but actually between the community, our neuroscience community. Franco will be here until the end of June, so everyone is welcome to engage with him. He's very curious about our community, our environment, our projects, so take any opportunity to talk one-on-one with Franco. And with any further ado, I will give the stage to Franco. Please help me welcome his talk.
Thank you, Ilaria. It was a really nice introduction. I don't know if I deserve it completely, but I try. It's true that my eater is not very normal. So I did psychology, and my thesis was on artificial intelligence system. You guys know traditional AI, what that means? How many of you know? So symbolic AI. So I developed a symbolic system, an expert system. Then I decided to change completely, and I started doing psychophysics for 5 years. Then I got bored. And then I said, I'm going to do physiology for a couple of years. And then I got bored. Then I'm going to do neuroimaging. And so every 5 years, I've changed what I do. And I'm saying this also because there are some of my students here. Thank you very much. This is the 4 hours of lecture today for them. Thank you for sticking around. So I appreciate the invitation. Thanks, Pina, and thanks, everyone, and thanks for... I would like to ask everyone, start with a question. How many of you have a Google account? Please raise your hand. Good. It's kind of 100%, I think, maybe 99. Okay. So what is Google #1 product? What would you say? It's you. Okay. So thank you. Normally people say search, mail, drive. It's us, right? So what they do, they collect data on us and they sell their data for profit. Okay. So so that's what brought us to realize that, coming from Texas, that's a very loaded sentence, made us realize that data are the new oil. Okay? What does it mean? It means that data are valuable not just for you and for us collecting the data, but are valuable for entire community. People are making, the biggest business out there are about data. So let's talk think about another thing. How many of you have a ChatGPT account? Come on, you can say. Don't be shy. All right. That's close to 90% too, right? So, okay, now same question. If you were to say, what is number one reason why 2 years ago this worked out? ChatGPT was made possible. Like a change in models, new algorithms, all the data. What else are you saying? Data? Is it about data? Data, data. So I'm going to push by saying that it's not just about data. Obviously, yes, it's about data, but it's about infrastructure. You know what happened to OpenAI? Microsoft built one of the largest supercomputing centers that exists for them. That's why Microsoft has such a large stake in the company. And because of that large data center and all the technical infrastructure that they developed inside the data center, they were able to use the data. So my point of view, it's not true that data are oil. Data on hard drives under your desk are not very useful. Data needs to put within an infrastructure that can be used by the community of scientists or researchers or business people that need the data, right? Google is the same thing. They collect data, they have data, but data without the infrastructure, the right infrastructure, is just numbers sitting on a desk. So here, for example, just 3 types of infrastructure. Google Maps, sure, geolocation, but software was written so that those geolocations are visualized, the pictures are put together, and everything is integrated and coordinated. Facebook, just for old people now, my students are looking at me like, it's Facebook. Facebook, same thing, right? They collect information, they link each other, all the users, and it's about infrastructure. It's about the software that links the data and brings the data to good use. And in neuroscience, we actually have a lot of types of data, many different modalities. Here it's a replot from 2014 of an older picture. And you can see we can collect data at very high spatial and temporal resolution up to lower temporal resolution. Some of these data sets, some of these measurements are good in humans, non-invasive, and some of them are good in animals. And we've been having a growth in major effort for data collection. The ping is one of the, I'm listing just a few that are the one that my lab has worked with. The CAM is an aging data set, I think was 8 to 88 years of age. The Human Connectome project was probably kind of iconic project that made everyone aware of the fact that this is possible. It's possible to collect really high quality data that everyone can use and reuse. The ABCD in the US now is collecting 10,000 children as they grow through life, through adolescence, later in life, collecting brain imaging, but also many other biomarkers. And many of you probably know the UK Biobank, right? 100,000 people, actually it's 500,000 of the UK citizens, right? But 100,000 of them have also brain imaging collected. So these are major efforts that with the understanding that probably the future will not be that the data you collect as a graduate student in 5 or 4 years in a lab, it's going to be the killer experiment that's going to change science. We need to scale what we're doing. How do we scale neuroscience? How can we get a graduate student to do more during the PhD? How do we get a postdoc to arrive in a lab and not have to just work with a script? So all these projects are becoming quite expensive in terms of data storage and infrastructure. So just the UK Biobank, it's expected by the end of the year to be over 40 petabytes. I remember the first time Stephen Smith presented, Stephen Smith at Oxford led the neuroimaging part and just came at a human brain mapping and said, hey, yes, we're gonna open this, we're gonna give you 100,000 subjects. And I was thinking, will I download them? Am I gonna download 100,000 subjects on a laptop, right? So obviously the future is not the past, right? So obviously we need to change the infrastructure that we're using. We need to start thinking about infrastructure. We need to start thinking about what we do with data. We need to start thinking about when we collect our data, how can our data be usable and helpful for others? It's one of the things that we've been pushing. Obviously, the future is probably going to move to the cloud with the sensitivity that you need for the data, the privacy that you need, might move to public clouds or private clouds. So AWS, it's one of the clouds we use. Jetstream, it's one of the public cloud, is funded by the NSF. It's built by researchers, been actually up and running for over 9 years now. It's a very successful project. And you can apply for funding and you can run on the cloud for free. And then Frontera, so Texas is #1 supercomputing center in the US for academic use. Frontera is currently the best supercomputer, the fastest supercomputer. And they're building a new one now that will be AI. They're building a new data center actually, because it was just qualified as a research facility. That means that you guys know the Arecibo telescope. You know how telescopes work, right? So telescopes are funded by, for public use. And then there's grants that support the access to telescopes, right? So there's a initial seed funding to build it. And then there's funding around so that you can use the telescope. If you're an astronomer, you can study the stars. TAC is becoming one of that, right? So they're building a campus, new supercomputing center, where it will be supported by other researchers applying for funding to use the center. So it's going to be a perpetuity. One of the problems of research cloud is that the grant ends and the cloud ends, right? Whereas this new model will keep everything going. So a couple of years ago now, the Biden administration made a statement about sharing data. And that changed the way the NIH in the US is asking us, funded by the NIH, to share our data. We have to have a data sharing plan, not a data management plan, which we had to have before. It's a data sharing plan. How and when are you going to share the data? Is that the same here in Switzerland? So there's nothing like that? You don't have to share your data with the community? You do have to share. You don't have to have a sharing plan. You have to share. And do you have infrastructure from the government to share data? Or is it up to you how you share it and where you share it? My understanding is Europe is moving really well in this direction. I think they're building clusters and infrastructure for data sharing because they understand first that this is really valuable and we're really throwing data down the drain, right? Because we're not standardizing it, we're not organizing it, we're not labeling it, and we're not sharing it. Right? I'll talk a little bit about AI later, but we just had a beautiful talk from Alex Pouget here in class for this morning. And it is the case that if today you are a person interested in using AI, in developing AI, you're a computational, you actually cannot do the research you want to do. Because the size of the model is such that we don't have infrastructure in research to tackle the models. So we have to rely on OpenAI and other companies, the one that leave models free to use or maybe low enough for price for researcher. Right? But we have lost the ability to do research on AI because we have not invested in infrastructure. So as a new graduate student or a postdoc, there's a lot of things that these new requirements for data sharing are bringing. It's in a world where you have to data management, you have to, pre-process thousands of data sets, if you're using these large new data sets, you need to look at quality control. How do you do quality control when you have 10,000 children of the IBDC? How do you do data analysis? Do you launch your script one after the other? Do you like parallel 4, parallel 18? How do you do all that, right? You have to learn how to run clusters. How many of you here use supercomputing clusters? Good, good. You have to learn how to run clusters. Do you guys have a data management system, or do you develop your own data management? Right? You just put the file somewhere and they get deleted. Some people do a cron job so that you touch the files and they don't delete them, or don't tell them to your supercomputing system. So big data needs technology. It needs glue. It needs that glue that connect the data to supercomputers, connect the supercomputers to the researchers. So a few years ago, I came from Stanford University to Indiana University. I was working on white matter, computational neuroscience, but I had this idea, hey, I would really like to build a platform like Facebook where there's data and people can use the data instead of using pictures, and everything is managed. People don't have to think about which one is the file, is it the right version? It was kind of a crazy thing, but over the next 9 years, we have developed BrainLife. This is the current version of BrainLife. There's a new one coming. Here I showed, I'm showing now how to visualize on the cloud some brain connection. What does BrainLife do? It takes data from scanner. PET is coming. We now do MEG, EEG, and MRI. It standardized the data. There's a system called EasyBeads. I think I have a slide later about it. There's a system called EasyBeads that takes the data from DICOM into beads, the brain imaging data structure. That can be pushed to OpenNeuro, or can be pushed into our private BrainLife project. Then if you're someone that writes analysis code, you can come with your code and publish it on the platform so that it becomes usable for others. Or you can use code that others are already published. For example, we have fMRI prep, there's QSI prep, there is MRTrix and different FSL-based systems, and you can use them for free. So the idea is that it should be a platform that connects the measurements machine to the type of research that people want to do. And so that ideally, graduate students and postdocs find the code they need to use, and they can just use it without having to think. Actually, the other day we had discussions about versions of MATLAB on different OS systems, and the same code doesn't do the same thing, right? So here we run Dockerized and systems that run via Singularity, can be deployed on different clusters. What does the platform really do in the back end? It takes data, it finds supercomputers that are available across the whole network in US. We're connected to Pittsburgh, TAC, Indiana University, and San Diego Supercomputing Center at the moment, and now we're getting into AWS. And there's a ranking system that finds which one is more free and moves your data there, process the data, returns the data with the results, and puts the data into the database, and you see them through the platform. You can write it, you can write scripts to run if you don't like interfaces. I'm not an interface person, even though I spent 9 years now developing interfaces. I like scripting, so you can do scripting, okay? And then you first process the data, and after you process the data, you can move the outputs of the data derivatives into Jupyter notebooks, and you can do machine learning or statistics on it. So these are the data modalities that currently are covered: anatomical, functional, diffusion, MEG, and EEG. Because of that, you can get surface analysis, brain volume, you can build networks and study white matter with different methodologies. So when I started, I did the thing you're not supposed to do, right? I was starting my tenure. I had like a Nature method paper doing white matter. I was supposed to continue to do that. I did, right? But I also tried this leap. And I was probably very lucky because when I started, none of my graduate students wanted to work on this. They wanted to do networks. That was what was cool. But after 9 years now, things have changed. Maybe not here yet, I don't know, right? I'm just looking at the faces, right? But in the US now, some of the largest projects, funded projects, are requiring large infrastructure systems because we are trying to scale up the question we ask. And I'll show you a couple of the new projects that have been funded. So the idea was, hey, there's all these problems having stones, and maybe if we organize them through infrastructure, they can get actually into becoming stepping stone for success for all of you guys. So I started with Soichi Hayashi. It was me and Soichi, my graduate student like Karen. Bradley actually, funny story. Bradley was a graduate student, interviewed with me, and then the interview went really well. After the interview, he comes back to the room, Professor, I just want to say one thing. I really don't want to become a programmer. Because, obviously he knew what I was doing, right? He said, no, don't worry, I do a lot of applications. I like applications. And guess what? He became the best programmer. And he's now an AI engineer and Novartis, right? So he was the one that took the lead when Soichi left, and then Hannibal is currently the graduate student that is leading most of the project. So it's a project done by researchers, for researchers. It's not always working super great. The supercomputers are busy, they're free. You can, in theory, attach yours. We have several, the Centre du Cerveau at Paris, they have their supercomputer attached to it, and they're doing, there's a Vanderbilt University, they attached their supercomputer. And I think we were talking to do something here, but I think my team was busy. Yeah. We need to get back to it. So EasyBits. Dan Levidas was another graduate student working in a lab doing affective neuroscience. He got bored and then came to me and said, hey, I don't think this is what I want to do. I think I want to be a developer, a data scientist. So we developed a system that takes DICOMs and then guides you. So you remember what I told you I did? I did an expert system, right? A long time ago. Okay? You'll see. EasyBits is like an expert system. Takes your DICOMs and provides for you a guess of how the DICOMs should be mapped into bids. And if you see that there are things to change, then you have an interface to change it. Once you do that for one subject, say you're studying a new study, once you do that for one subject, you can then download a template. And then for all the new subjects that are doing the same protocol, you can upload the DICOMs, spread the template, and it will fill up everything following the template. So here's what happened, especially after and during the pandemic, right? I remember during the pandemic, we constantly monitor who logs in the platform because we check, a human checks who's logging in, we have information. And during the pandemic, there was March 15, 2020, spike followed that date in Brain Life because the lab closed. People didn't know what to do. They wanted to analyze data, could not access their computer, and they started looking at Brain Life. Over the past 9 years, we have about 4,700, a little bit over that, user accounts, about 100 active users per month, not always the same. And over the years, we've benchmarked and validated the platform for a lot. In fact, the paper came out last year. Right? We just published the paper last year because we spent many years developing a system that was deep in what it was providing, but was also valid in what it was doing. So Ilaria, Vindrich, and I did a couple of studies, one of which used Brain Life, and we mapped and understood, you guys know this, right? When I give this talk, not just here, and studied the connectivity of the attentional system. The first study was not done with Brain Life, but the second study in humans was done with Brain. After that, Sophia Vinci-Bucher. Sophia was a graduate student in developmental psychology, and she's smart. She said, I need to understand that. Right? So we applied for a grant. I told her no. When she applied for my postdoc in my lab, I said, no, what do we do together, right? But no, we wrote a grant 3 times, right? But the third time she got it, right? And as soon as she got the grant, I left. So she stayed back in Indiana. I left money for her. She did a whole operation, collected data, beautiful study. So this is just one paper that came out of that study, but we're publishing the whole data set soon. So it's a very nice study. I'll tell you what we did. We scanned Ilaria on Monday, diffusion MRI. How many of you know diffusion MRI? Okay, good. So you know what I'm talking about. Diffusion MRI, right? And then we spent the rest of the week training Ilaria on a new task, right? So Ilaria was learned, well, I didn't, right? Sophia did, right? She learned how to draw new symbols. And we measured how long it took to draw, and then we measured also later some reaction times. Then we measured the white matter on the major white matter tracks, about 60 of them, right? Major white matter using BrainLife, the pipelines on BrainLife. Then we ran some machine learning. It's quite simple type of machine learning. It's not a deep network. And we predicted who was a good learner and who was a bad learner. So from the Monday scan, we predicted who was going to be a good learner and a bad learner. Ilaria was. All right. So yeah, here's the model results, and we predict with pretty high accuracy. So prediction is one of the things I've been working in the applications, and this is another study. How many of you have had a concussion? Had a concussion last year? I was rollerblading. Yeah. So what's the thing when you get a concussion that is really annoying? I mean, head hurts and everything. If you get the flu, you know that is 7 days with medicine, 1 week without, right? Or is it the opposite? So do you know that it will end? With concussion, there is this very annoying thing that you don't know when symptoms will stop. It's a very difficult prediction. We have no clinical tools that can tell a patient when they will feel better, then they will go back to work. So I work with my colleague, Julia was postdoc in the lab, and Nicolas is a colleague at Indiana University. We actually use a data set from the Department of Defense and NCAA, the College Association for Sports in the US. They collected data on 13,000 something students, which about 200 of them had two variables, had diffusion MRI and had acute measurements, right? So we measured students after they had a concussion within 24 hours to 48 hours. So during the acute phase, an idea we had is that during that acute phase, there's enough inflammatory system, doesn't matter where, that we should use a machine learning system to predict when they're going to back to work. And the good thing is that they measured going back to work, going back to school, right? So, and we ran actually, we thought we were going to do deep learning, but then 13,000 students thought that was going to be super cool data set. Turns out it was only 200, so we did a simple machine learning, logistic regression, but still we predicted pretty well. And the interesting thing is that the white matter tracks, the long connection between different areas, that's what the most predicting signal, right? If you look at signal in cortex, didn't predict really well. If you look at signal in the deep structure, didn't predict very well. So we were able to, I guess, accumulate the signal, the inflammation process, all of that across. This is the best, currently the best predicting model for that question. It's better than any clinical tools. We're trying to run a clinical study now, trying to get funding to get a clinical study to actually expand from 200 to more data set and be able to generalize. So I work on what matters a lot. I study these major tracks. I study development. I study how they change during aging. One of the things that I'm interested currently is that we can name, people agree on 21 tracks. We just came out with I don't have it here, a nice little review, 21 tracks for the 21st millennium. Like those ones we trust, right? And but there's about 60 of them that we can routinely map automatically that people use. Of those tracks, we do not know or understand well their function. What type of information are they carrying? What type of transformation are they making, right? So if there's a track that starts in one part of the brain and carries information to the other part of the brain, what change in processing is happening? So with Alex Huth, a colleague at UT Austin, and Suna is a graduate student with us, shared. We're looking at, Alex studies semantic maps, how semantics is distributed across the brain. So we're matching his semantic maps to determination of the white matter tracks and trying to understand what type of semantic information the tracks map. Another study we're doing is with Kim Ray, and I'll show you the picture. Kim is a research assistant professor in my lab, and she's an expert on meta-analysis. How many of you know Neuroscience? But Neuroscience. So Neuroscience is a system that you can go and you ask questions like, where is attention or reaction time, and it gives you the brain location where from the literature is being reported attention. So we're now developing a new system that connects the white matter tracks termination in cortex, maps them onto the maps from, it's not Neuroscience, it's a better system with NGLR that we're doing. And it's really fascinating. The first thing we did here, we validated using the arcuate fasciculus. We know the arcuate fasciculus is about language. So here is the arcuate fasciculus, the maps in cortex of the frontal termination and the posterior termination. And here is what comes out of meta-analysis, right? The front is about semantics, sentence, language, words. The back is about working memory, phonological understanding, naming, etc. And we've done this with all the tracks, many tracks, and we can, you see how we get very nice. Actually, we clustered the tracks into groups by function. And but this paper should be coming out by the end of the year. It's really interesting. So Kim is a research assistant professor. So me and Daniela are two undergrads in the lab. The fact that we use the platform allows some of the undergrads to actually contribute to research. They can do quality control. They can easily use the platform and understand the brain. They don't really need to learn Python before they can access a lab and do research. Now, as I said before, tractography is not going to do it all, right? We can do some, and you can build a tool that does the best we can do today, right? But in the future, we need to work on solving problems. Tractography has multiple problems. Here is a bunch, for example, crossing problem. You don't know if fibers are crossing or kissing. That information cannot be resolved. So in 2022, the US, the Brain Initiative, put about $150 million on this new effort, right? In the past 10 years, the Brain Initiative put about the same on the cell census. How many of you know about the cell census and the Allen Brain Atlas? Sometimes that's more known. It's an NIH project, right? That the Allen kind of was running, trying to identify cell types in the brain, right? So that we would have a census of the different cell types. You understand that there's many types of cells that we don't know, right? So now, after they did that, now they started what is called Brain Connects. Brain Connects is about understanding the connections in the brain. So the project is funding different centers nationally. Each center is about $10, $15 million that are trying to do mice, they're trying to do macaque, they're trying to do marmoset, they're trying to do different types of modalities, trying to integrate the information across the species. So I am part of the Center for Mesoscale Connectivity, which is based in Minnesota. Camilo Gurbil is the director, and Stam Satiropoulos and Nottingham is involved, and Jababdi at Oxford, Carla Miller, there's Clay Reed, Sarah Hillbronner is actually, I have the picture of everyone. The goal is to understand how to integrate different types of modality and build priors for connectivity so that diffusion MRI can work better. Okay? So here's the group. I just said that Sarah, this is another cute story. Sarah and I wrote a grant 3 times in R01 where we wanted to do kind of this, right? And the reviewer were asking for more every time, more and more. And then Sarah said, well, let's give them more. So we wrote a $20 million center grant, and that worked, right? So now we're giving them more. Camille is the director, the administrative director. So we're studying just not all the brain. We're studying, focusing on just the connectivity between the parietal and the prefrontal. And we're doing different measures. We're doing in vivo MRI and ex vivo MRI in humans and macaques. So we're using 7 Tesla and the 10.5 Tesla that they have in Minnesota, super high resolution diffusion. We're doing PSOCT. How many of you know about OCT? OCT is how they take pictures of your retina. It's a very cool stuff. They scattered some light on the back of your retina. The light can penetrate the retina, and you can see all the layers of the retina. It's really cool. Well, folks, our colleagues in Minnesota, now they created something that looks like an ice cream maker, where you can lower the brain and you can shape the brain and you can image with the same technique, right? Entire slices of macaque now and human later. This is where year 1. We just, before coming here last week, I was in the year 1 report to the NIH. It's very exciting. So here is some of the picture we're getting. These are actually the picture that we submitted with the grant. So that's on top is the PSOCT, on bottom is the 7 Tesla DTI, and on this other side on top is the PSOCT, and then the 10 Tesla at that time is getting better and better. But we don't just do PSOCT, we also do different type. This is from the BU group in actually Shenzhen University in China. And they develop, it's called the Visor pipeline. They're able to track macroscopically and microscopically entire axons. Here is the whole frontothalamic connection. But you can actually track from the same data sets individual neurons. Obviously, this is very different data than what we have. Each one of the PSOCT brain, it's about 2 petabytes of disk. Okay? The Visor is also really expensive in terms of storage, right? So what we're doing, I do the technology for the project. We're developing new infrastructure for AI, for brain life, so that we can actually serve. We're supposed to share all this data. This data is going to become available for researchers, but how do you download 2 petabytes per brain? Okay? So it's a completely different way to think about it, right? You need to bring compute to the data. You can't move data to compute, which is the current model. All right, a couple of more things to wrap up and done. I've been working now for a couple of years on a project funded by the Wellcome Trust. As brain life became such a big thing, I noticed that many people were coming from Africa, Latin America, Asia, and data governance became a problem for me. Right? So I started working with colleagues in ethics and colleagues in the law school, and we got funded a project, but it's a 3-year project that will bring together researchers from Africa, Latin America, North America, and Europe. No Asia at this moment. And we're trying to understand the legal landscape, following the GDPR, many countries have changed the way data can be transferred between countries. We're trying to understand the landscape of that. We're trying to understand what are the cultural and ethical implications of some of the data we have. It's a very interesting project, takes a lot of time. The idea is that data governance normally is defined nationally. In fact, we have a nice paper. This is the early paper that got us funded. It's a 2022 paper. The idea is that we want to develop data governance frameworks that help researchers share data without fearing, because most of my European colleagues don't want to share data, don't want to read the GDPR. They're worried, right? They tend to be worried about what can happen. GDPR actually doesn't say that you cannot share data. You have to follow some procedure, and you have to make sure that you're doing it right way, but you can share data. So the vision is to It's a mental health and neuroscience project, so we have patients and patient groups involved so that they can speak their voice about what they want to be done with their data. During this work, I met Ebere and Damien. They're Nigerian. I work with them now a lot. Ebere just published the first Nigerian data sets on neuroimaging. It's from 1.5 and 0.7 scanners, clinical scanners, so it's not very high quality, but it's a statement that can be done from Nigeria, from Africa. And I started working in Africa. I go every year. So this was a 2024 academy in Lagos, Nigeria, and it was really fascinating experience. Last year, the academy was in Kenya, in Nairobi. I think this year we're going again to Nigeria. I think now it's actually the third year that we got funded. Thank you very much. I want to thank my, join us, visit Austin. Austin is great. It's in Texas. Texas doesn't sell itself very well, but it's actually a beautiful state. There's a lot of nature. There's no mountains, but there's rolling hills with very beautiful oak trees. You can climb, so there's creek beds in town, single pitch climbing all around town. My students don't know that. And this is the downtown. Half of the skyscrapers there were not there when I joined UT in 2020. Right? That's how fast it's growing. And yeah, beautiful place. And thank you very much.